Hey folks! In this video we are going to be looking at an example problem with an object on an incline which is accelerating. So not only is it moving, but it's changing its velocity as it moves. Let's go ahead and get started. Here we have, starting from rest, an 80-kilogram skier goes downhill and covers 15 meters of distance in 3.6 seconds. The skier moves with a uniform acceleration. We want to find the strengths of the normal force and the friction force exerted on the skier by the hill. Our starting point, of course, is going to be to identify our system, and here that system is the skier. We have a downward velocity, the skier is going downhill, and not only is the skier going downhill, but they are moving with a uniform acceleration, and so there is a downhill acceleration in the direction of the velocity, because we are getting faster. Now that we've added in our velocity acceleration arrows, we can draw a force diagram for our chosen system, the skier. Let's draw that dot in to represent the skier and then look at the forces exerted on the skier. When I do this, I like to draw in a little dashed line to represent the slope that helps me figure out where the normal force and friction force are. So with that, those are the subscripts I'll use. I have a downward gravitational force on the skier by the earth. I have a normal force on the skier by the hill in a direction that's perpendicular to the incline, and I have a friction force on the skier by the hill, and that friction force points uphill because the skier's velocity is downhill and they're sliding downhill. Let's make a list of givens and, not givens, unknowns yet. First we're going to draw in our sign conventions here, our reference frame. We're going to do our analysis with one of our axes parallel to the incline. That's labeled with the positive parallel symbol from geometry class. And then we have the direction perpendicular to the incline, and that's labeled with the positive perpendicular symbol from your geometry class. We want to then, once we've decided our reference frame, draw in components. So we have the perpendicular component of the gravitational force exerted on the skier by the earth, and we have the parallel component of the gravitational force on the skier by the earth. And we did that because the gravitational force is neither perfectly in the parallel or perpendicular directions, but rather it has some components in each direction. And I'll remind you also that we chose to draw the perpendicular component first, because if you do that, then the 25-degree angle, which is the angle of incline, shows up in your force diagram as indicated on the diagram. We can also add in the fact that the normal force here is balanced out by that perpendicular component of gravity. Now we can make our list of givens and unknowns, and let's see, what do we know? We've got the mass of the skier is 80 kilograms. We have theta, the angle of incline, is 25 degrees. We have the initial velocity, v sub 0, is equal to 0 meters per second. We have the initial position, x sub 0, is 0 meters. We have the final position, x sub f, is 15 meters. And we have the time is 3.6 seconds. And we're looking for the three forces in the force diagram: the gravitational force exerted on the skier by the earth, the normal force exerted on the skier by the hill, and the friction force exerted on the skier by the hill. And we're looking for their strengths or their magnitudes specifically, and so I left the vector arrow off of our capital F's there in the unknown column. Let's find that gravitational force first. We have our gravitational force law, which relates the mass of the object and the force felt by that mass in a certain gravitational field, with the law shown there. Gravitational force on the skier by the earth is equal to mass times the Earth's gravitational field strength. The mass of the skier is 80 kilograms. The gravitational field strength on Earth is 9.81 newtons per kilogram of mass, and so the gravitational force is 784.8 newtons. Cool, we've got that gravitational force. Next, before we do any sum of force equations, we want to take our force components and find those using some trigonometry. And so let's start with the sine of the angle theta, and we'll do the cosine next. So sine of the angle theta is opposite over hypotenuse. In the right triangle for the gravitational force drawn on our force diagram, the side of that right triangle, which is opposite the 25-degree angle, is the parallel component of gravity. And the hypotenuse is the full gravitational force. And so we replace our math in line 1 and translate it into physics in line 2. And after we've translated into physics, we are going to rearrange that equation so that the unknown, the parallel component of gravity, is by itself on one side of the equal sign, and Everything else is on the other side of the equal sign. We did that by multiplying each side of the equation by the full gravitational force exerted on the skier by the Earth. When we plug in numbers, the gravitational force on the skier by the Earth is 784.8 newtons, the angle theta is 25 degrees, and plug all that into a calculator, you find that the parallel component of the gravitational force must be 311.7 newtons. There we go. Let's go ahead and look at cosine now, and we can find the other component of the gravitational force. In general, cosine is defined as the adjacent side of your triangle divided by the hypotenuse of your right triangle. And in this case, the side of the right triangle that's adjacent to the 25-degree angle is the perpendicular component of the gravitational force, and the hypotenuse is still the full gravitational force. And so we take our math in that first line and we've translated it into physics in the second line. After we've translated into physics, we can plug in, or we can rearrange first, get the perpendicular component of the gravitational force by itself on one side of the equal sign by multiplying the full gravitational force on each side of the equation to get it out of the denominator. And now we can plug in values. That gravity force is 784.8 newtons. The angle is still 25 degrees, and plug 784.8 newtons multiplied by the cosine of 25 degrees into a calculator, and you'll find that the perpendicular component of the gravitational force on the skier by the Earth is 711.3 newtons. So there we go. We have our force components. We have the gravitational force. All of that looks good. So the next thing we're going to be looking at is writing some sum of forces equations, and we'll do that in both the parallel and perpendicular direction. We'll start in the parallel direction. I've highlighted the positive parallel direction on our sign conventions on our reference frame there, and I've also highlighted on the force diagram all of the forces which point either in the positive or negative parallel direction. So we can see that the friction force and the parallel component of the gravity force are both highlighted in the force diagram. And so we're going to write our sum of forces in the parallel direction must be equal to the parallel component of the gravitational force plus the friction force, and that's the full friction force. From here, we are not just moving downhill, but we're also accelerating downhill. We're getting faster in that direction as we move. And so the sum of the forces in that direction must be equal to mass times acceleration. And so we're going to replace sum of force with mass times acceleration. Now that we have our vector equation written, we're going to write a scalar equation where we're going to get rid of the vector signs above each of the vectors, but we are going to write either a plus or a minus in front of the scalar so that we can indicate direction. The acceleration is in our positive parallel direction, so we get a plus in front of the term ma. The parallel component of the gravity force is also in our positive direction, so it gets a plus in front of the f sub g parallel. And then the friction force is in our negative parallel direction, so it gets a minus sign in front of the f sub f. And the thing that we can find with this eventually is going to be the friction force, and so we can do a little bit of algebra to rearrange this equation to get the friction force by itself on one side of the equal sign. But now we're kind of stuck because we don't yet know the acceleration. And so I'm going to stop here with this equation, sort of put it in my back pocket, and pull it out later when we are ready to evaluate with that equation. Let's go ahead and write our other sum of forces equation. We're now going to add the forces in the perpendicular direction, and so we have a normal force on the skier by the hill and the gravitational force on the skier by the Earth, that perpendicular component. Those are both in our positive perpendicular directions. And again, I've indicated the direction that we're looking at by highlighting the positive perpendicular direction on our reference frame, on our sign conventions, and on the force diagram, I've highlighted all of the force which point in that direction, all the forces which point in that direction. And when we write our sum of forces equation for the perpendicular direction, it looks something like this. The first line there, the sum of the forces in the perpendicular direction must be equal to the vector sum of the normal force on the skier by the hill plus the gravitational force on the skier by the Earth, that perpendicular component. Now, in the perpendicular direction, there is no acceleration. The skier is not jumping off of the hill, nor are they digging themselves into a hole in that hill. And so the sum of the forces in this case is not equal to mass times acceleration, but rather is equal to 0. So as our second line there is replacing the sum of the forces with 0. Our third line is to go from a vector equation to a scalar equation by removing the vector arrows above the F, but putting a plus in front of the positive scalars, which in this case is the normal force, and putting a minus in front of the negative scalars, which in this case is the perpendicular component of the gravitational force. Adding that perpendicular component of the gravitational force over to the other side of the equation, we can see what we indicated on our diagram, that the normal force on the skier by the hill must be equal to the gravitational force on the skier by the Earth's perpendicular component. And we know that perpendicular component of the gravitational force at 711.3 newtons, as we found in the yellow box, and so the normal force must also be 711.3 newtons. And there we go. So what's left is we want to find the friction force, but in order to do that, we're going to need to come up with a value for the acceleration. We can't do that using Newton's laws, so we are stuck with the approach we have on the screen so far. However, we can go back to what we learned earlier in our uniformly accelerated motion unit and use some of those principles to find the acceleration. Use some of those kinematics ideas to find the acceleration. I'll remind you that there were three main kinematics equations that we came up with through our labs and through looking at graphs. We had an equation for the velocity, an equation for the position, and a relation between the velocity and position which didn't depend on time. Which is going to be the useful equation here? It's the one that only has one unknown value. So let's bring our givens up onto the screen again so we can remind ourselves what it is that we do know. And let's go through that first equation. We do not know the final velocity, and so that's one unknown. We don't know the acceleration, that's two unknowns. We do know the amount of time it takes, and we do know the initial velocity. So that's an equation with two unknowns right now, and so that's not going to be a helpful equation. Let's look at the next equation. We do know the final position, it's 15 meters. We do know the initial position, it's 0 meters. We do know the initial velocity, it is 0 meters per second. And we do know the amount of time we're looking at, it's 3.6 seconds. We don't know the acceleration, and again, we do know the time. And so this is an equation which only has one unknown. And for that reason, we should use this equation to find the acceleration. And so I'm going to write that equation over to the right there, and we're going to first rearrange this equation to get a by itself before we plug in numbers. In order to do that, I'm going to subtract the initial position over to the left side of the equal sign, and I'm going to subtract the term that has the initial velocity times time over to the left side of the equal sign, so that all terms without an a are on the left side of the equal sign, and then the one term that does have the a in it is on the right side of the equal sign. From here, I'm going to divide each side of the equation by 1/2 t squared, which is everything in that term on the right except for the acceleration. And when we do that, we end up with 1/2 t squared in the denominator on the left side of the equal sign, and the 1/2 and the t squared is been divided out on the right side of the equal sign. And so now we have an expression for our acceleration. We can plug in all of those given values, the final position of 15 meters, the initial position of 0 meters, the initial speed of 0 meters per second, the time of 3.6 seconds, and in the denominator, half of 3.6 seconds squared. Plugging that all into a calculator, or simplifying that a little bit first, that just does reduce down to 15 meters in the numerator and 6.48 square seconds in the denominator, and then 15 divided by 6.48 gives us an acceleration of 2.31 meters per second squared. And so now we have our acceleration. And we can go back to the pink box now, because now in that pink box the only thing we don't know is the friction force, because we have this acceleration now from the previous screen. And so if I go to the pink box equation and plug in our values now, we know the parallel component of gravity is 311.7 newtons, we know the mass is 80 kilograms, and we know the acceleration is 2.31 meters per second squared, and that leaves us with a friction force of 146.5 newtons. And now that I have my friction and normal forces, which is what I was looking for, I'm going to put boxes around those so I can say, yes, I did it, here are the values. And that finishes the problem. We'll do a quick recap here on what we did. We identified our system, we drew velocity and acceleration arrows, we drew in a force diagram for this skier, We drew in the sign conventions for the parallel and perpendicular directions. We broke up our gravitational force into components, and that was what's on the left there. We then computed the gravity force and its components using our gravity force law and some right triangle trigonometry. We then wrote net force equations for the parallel and perpendicular directions and used those to find the friction and normal force. We did have to take a quick aside into kinematics to find our acceleration value, and once we had that, we were good to go. So that concludes this video on this example problem. I hope that's helpful, and please let me know what questions you have.